Hey, there's some classic Weezer for you before we get started on our lecture for March 27th, Kin 225. And here's the start of your PowerPoint for today. So today's class involves a review of carbohydrate metabolism, some questions about diabetes, and the concept of the glycemic index. So this refers to the amount of sugar or glucose increase that you get in your blood after eating certain foods. So if you eat a food that has a low glycemic index, it results in a slow and low blood glucose increase. And if you eat foods with a high glycemic index, it gives you a fast and high increase in glucose. And both of those types of carbohydrates will affect exercise performance differently. So I'm going to go over that concept today, and then I have some practice questions, kind of review questions from previous quizzes. So your third quiz for the course is canceled, and I'm going to give you a couple of practice quizzes instead. Before I go on, I have these reminders that your Lab 6 is due on Monday and Lab 7 is due a week from Monday. So we will be posting a PowerPoint presentation for the anaerobic threshold, which is the topic of your Lab 7. So some review questions for you. What is the most common isoform of glucose transport protein in skeletal muscle? And the correct answer here is D. It is your GLUT4s. So your GLUT4s are these glucose transport proteins that are located inside muscle fibers. And when you exercise or when insulin binds to the muscle fiber membrane, those glucose transport proteins will go to the muscle fiber membrane and allow glucose to come into the muscle fiber. So those glucose transport proteins essentially are important for getting glucose inside the muscle while you're exercising or after you've eaten a meal when your insulin levels are high. What causes glucose transport proteins to migrate from inside the muscle to the sarcolemma or the muscle fiber membrane? So I kind of answered part of this question on the previous question. So the correct answer here is elevated insulin levels. So insulin gets released after you've eaten a meal. When your blood glucose levels are high, it will bind to receptors on your muscle, and that stimulates glucose transport proteins to go to the membrane and allow glucose to be taken up by skeletal muscle. Which of the following cannot take part in gluconeogenesis? So your options here are lactate, glycerol, fatty acids, and amino acids. And the correct answer here is C, fatty acids. Lactate, glycerol, and amino acids can all go to the liver during exercise and be converted into glucose. Then that glucose can be used to replenish your blood glucose stores and provide your muscle with glucose for energy. So glycerol and fatty acids both come from breakdown of triglycerides or fat in adipose tissue, but only the glycerol part can participate in gluconeogenesis, whereas the fatty acids, they cannot be converted to glucose. Now I have a question here about the proper order for progression of type 2 diabetes. So you can see I've got listed in bullet points different stages of this condition, and I'm going to go over this on a piece of paper here with you. So the first thing that would happen here to develop type 2 diabetes is to have a high food intake and lack of physical activity that leads to high blood glucose levels. So that's your first step. And those blood glucose levels, if they're chronic, then that can lead to development of type 2 diabetes. The second step here is that the blood glucose would stimulate high release of insulin from the pancreas. So that's your second stage. The third stage is that your muscle is exposed to chronically high levels of insulin. So that's 3. And recall that insulin has to bind to the muscle membrane to get glucose inside the muscle. The next step here is that muscle would lose its sensitivity to insulin. So the insulin essentially stops working on the muscle. To compensate for that, your body will try to release more and more insulin to get that glucose into the muscle. And at that stage, the pancreas from which the insulin is released gets overworked and can no longer produce sufficient insulin. So that's your 5th stage. And then your last stage is that if your pancreas is no longer producing sufficient insulin, then you have to take insulin injections. So that would be your last step here, number 6. So there are all your steps and the answers to this review question. So I've got a couple of other questions here that deal with glucose uptake or type 2 diabetes or diabetes in general. So the first question is, identify 2 physiological changes that occur with exercise training to alleviate type 2 diabetes. So I'm asking for 2 here, but you can probably list about 4 or 5 changes. So I'm going to go to the whiteboard for these. One change you get is an increase in glucose transport proteins inside your muscle. So that'll allow greater glucose to go into your muscle in response to insulin or in response to exercise, and that alleviates that condition of high blood glucose. Another change you get with exercise training is simply an increase in muscle mass. So muscle acts as the greatest glucose consuming organ in the body. So if you're trying to reduce your blood glucose levels, it's good to have high muscle mass because that's where most glucose is used. You can also say increased capillarization of muscles. This would allow greater glucose to be delivered through the blood to the muscles. You can also say increase in any of those mitochondrial enzymes that are involved in glucose oxidation or the aerobic metabolism of glucose. So you can say increase in pyruvate dehydrogenase. You can say increase in Krebs cycle enzymes. Or you can say increase in enzymes of the electron transport chain. I'm just going to put ETC for the short form of electron transport chain. So theoretically, any of those changes would help you clear glucose from the blood and lower your blood glucose levels and alleviate type 2 diabetes. So the next question I have up here deals with type 1 diabetes. And the question here is, why is it recommended that a type 1 diabetic not inject insulin into a muscle shortly before that muscle is exercised? So the problem with type 1 diabetics is that they can't produce insulin from their pancreas, and so they can't get glucose into the muscle unless they take insulin injections. So it's generally recommended that they don't inject insulin in close proximity to an exercise session, and the reason being that recall that with muscle contraction or exercise, you get that pool of glucose transport proteins that goes to the muscle fiber membrane. And then if you injected insulin, you get a greater amount of glucose transport proteins going to the membrane. And in this case, the problem here is that you're getting too much glucose uptake into the muscle, and you end up having a very low blood glucose level left over. So this condition where your blood glucose level is extremely low is called hypoglycemia. Hypo just meaning low, and then glycemia referring to your blood glucose levels. So that condition of hypoglycemia can lead to passing out, feeling faint, essentially because your nervous system, your muscles, your nervous system, so your spinal tissue, your brain especially, depends on glucose as a fuel source. So if you have this condition of hypoglycemia because of too much glucose uptake into the muscle, it can affect the function of your brain. Now, does insulin stimulate or inhibit mobilization of fats from adipose tissue? And the correct answer here is B. It inhibits the mobilization of fats from adipose tissue. So insulin has the effect to pack things away. So it would pack away fats rather than mobilize them from adipose tissue. Now I'm tying this into the topic of the glycemic index and what it does to insulin levels. So this next question is it better to stimulate fat oxidation or carbohydrate oxidation in muscle during long duration exercise, and then why? This is a bit of a review question. It would be better to stimulate fat oxidation because this spares glycogen, so it spares your carbohydrate stores, and it's ultimately glycogen depletion that causes fatigue during long duration exercise. So this slide introduced the concept of the glycemic index. So as I mentioned at the start of the presentation, the glycemic index of a food indicates the blood glucose response after consuming that food. So a high glycemic index in a food results in high blood glucose levels and also high insulin levels. So the problem with regards to endurance performance would be this high insulin level. Recall that the high insulin levels, that inhibits fat oxidation. So theoretically, you would have lower fat oxidation if you consumed a high glycemic index food, and that would necessitate higher carbohydrate oxidation and faster depletion of glycogen. So some sports nutritionists recommend consuming low glycemic index foods before doing exercise, especially endurance exercise, because the lower blood glucose response will result in a lower insulin release, greater fat oxidation, and less carbohydrate oxidation. And that would allow sparing of muscle glycogen during your exercise session. So this table shows you foods with different glycemic indexes. So you have at the top some low glycemic index foods, so apple juice, lentils, chocolate milk, spaghetti, bananas, moderate glycemic index foods, and then some of your higher glycemic index foods. So that would include potatoes, Gatorade, white bread, and cornflakes. So we've done a number of studies where we've assessed the glycemic index of carbohydrates that are consumed before exercise performance. So we focused a lot of our research on soccer players. So this shows a soccer player with, if you can see it, it's a portable metabolic cart that that the soccer player is wearing. And that portable metabolic cart allows us to assess oxygen consumption and carbon dioxide output while the person is exercising and moving around. And from those measurements of oxygen consumption and carbon dioxide output, you can estimate your respiratory exchange ratio, which can be used to estimate fat and carbohydrate oxidation. So we've used this to assess carbohydrate and fat oxidation during exercise after consuming either high or low glycemic index foods. So these graphs show results of one of these studies. So this is consumption of low versus high glycemic index sport nutrition bars before a simulated soccer match. So focusing on the top graph, you can see the low glycemic index and high glycemic index conditions. This is before the onset of the simulated match, and then the simulated match lasted 90 minutes, just like a real soccer match. You can see that before the match started, this is before the match, but after consumption of the low glycemic index or high glycemic index sports nutrition bar. The high glycemic index bar results in a greater elevation of insulin before the exercise session. So recall that the greater elevation of insulin, it tends to pack away fats into adipose tissue, and it prevents the mobilization of fats from adipose tissue and inhibits fat oxidation. So on this next graph, you can see the fat oxidation values for the low glycemic index and high glycemic index conditions. And again, on the bottom, this is time during the exercise test. So this is time during a simulated soccer match. So throughout the simulated soccer match, you can see that the low glycemic index condition, if the low glycemic index bar was eaten before the soccer match, it resulted in a higher fat oxidation during the soccer match compared to consuming a high glycemic index bar before the soccer match. And then down here, we have the results for carbohydrate oxidation. So as expected, the low glycemic index condition resulted in a lower carbohydrate oxidation throughout the soccer match compared to the high glycemic index condition. So theoretically, this would be beneficial because it would prevent glycogen depletion later in the soccer match. This next graph is from a different study we ran where we actually took muscle biopsies late in a simulated soccer match. You can see it was at the 75-minute mark of a soccer match. And again, this was after feeding players either low glycemic index foods or high glycemic index foods before the soccer match. And then the control condition is just feeding them nothing. So you can see the glycogen levels at the 75-minute mark were highest after the low glycemic index condition, next highest after the high glycemic index condition, and as expected, lowest after consuming nothing before the soccer match. So again, this would theoretically provide you with a performance benefit if you could have higher glycogen levels, late in a soccer match or any other endurance exercise performance. So this is a summary of those previous slides on the glycemic index. So low glycemic index carbohydrates result in less insulin release, and this allows greater fat oxidation and lower carbohydrate oxidation at the muscle. And this would allow sparing of muscle glycogen and could theoretically enhance your endurance performance. So a controversial area with high versus low glycemic index carbohydrates is traditionally sports nutritionalists have recommended that high glycemic index carbohydrates be consumed in recovery from exercise to enhance glycogen resynthesis. So this figure that I had up last day shows what's happening, if you have high insulin levels after an exercise session and how that can help take up glucose from the blood into the muscle. And this would allow a faster rate of glycogen resynthesis. So theoretically, a higher glycemic index carbohydrate would allow a greater release of insulin and enhanced glycogen resynthesis post-exercise. The second bullet point, though, kind of raises controversy around which carbohydrate is better to consume post-exercise. So this particular study showed that if you consume the low glycemic index carbohydrate after exercise, it helped with the replenishment of intramuscular triglyceride stores, so intramuscular fat stores, which are also an important energy source for endurance exercise performance. So we ran one of the few studies where we actually assessed the effects of low glycemic index versus higher glycemic index. Again, this is sport nutrition bars, and this is the effects on cycling performance. So in this study, we used a low glycemic index sport nutrition bar or a moderate glycemic index sport nutrition bar. And we gave them to cyclists before they did a 7-kilometer time trial. So this graph represents their time trial performance. So you can see the low glycemic index bar, the moderate glycemic index bar, they both improved time trial performance over a placebo condition. So the placebo condition is basically a condition where we gave them it was diet Jello, but we told them it was a sports gel, but it essentially contained no calories. So either one of the sport nutrition bars improved time trial performance. So this is 7-kilometer time trial performance in cyclists with a lower time during the time trial representing an improved performance. Now, after this test, we gave the participants either a moderate glycemic index bar or a low glycemic index bar during recovery from exercise. And then we had the cyclists come in the next day and do the same time trial performance. So this is the next day doing a 7-kilometer time trial performance. Again, consuming these bars after the previous day's exercise. So you can see that the low glycemic index condition resulted in the best recovery performance compared to both the moderate glycemic index and the placebo condition. So giving a low glycemic index sport nutrition bar in recovery from the previous day's exercise performance was better than giving a moderate glycemic index bar or giving a placebo after the previous day's exercise. This is for improving next day exercise performance, again in a 7-kilometer time trial for cyclists. So now I have these review questions. These are kind of questions that I've cut and pasted from previous quizzes from other years of this course. So these questions provide you a review on energy systems and also respiratory quotient, so carbohydrate versus fat metabolism. So the first question it asks gives an example of a hockey player who plays 2 30-second shifts separated by 1 minute of rest between shifts. And assuming that they skate at full intensity during their shifts, what energy system would be dominant during each of these shifts, and then explain your reasoning. So the phosphocreatine energy system provides phosphocreatine for about 30 seconds before it becomes fatigued. And then you switch to dominance with the anaerobic lactate energy system. So the predominant energy system during the first 30-second shift would be the phosphocreatine anaerobic energy system. And then you recover 3 minutes for that energy system to fully recover. So by having only 1 minute rest between shifts, they won't have full recovery of that energy system. So the second 30-second shift, they'll still use their phosphocreatine energy system, but the lactic acid anaerobic energy system will become dominant during the second shift. So the second question, how would you expect respiratory quotient or RQ to change from the start to the end of an ultra marathon? So this is 80 kilometers of running, and explain how the RQ would be different for someone consuming a carbohydrate beverage during the marathon compared to someone who consumed only water. So at the start of your marathon, your RQ would be higher than at the end of the marathon, because by the end of the marathon, you're probably running out of glycogen stores and your body is shifting to oxidize mainly fats at your muscle. So your RQ would expect to decrease quite dramatically from the start to the end of an ultramarathon, mainly because you're running out of glycogen, and so you stop oxidizing. You switch from oxidizing carbohydrates to predominantly oxidizing fatty acids in your muscle. Now, if you consumed a carbohydrate beverage during the marathon, your respiratory quotient would remain higher than if you consumed water.